Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, lesson 34. Are all parabolas congruent? Okay, before I begin this lesson and the opening exercise, we were given a website URL in the teacher edition. So I've hovered over the address here so it shows the whole thing so you can see it in the video. And you can go to this website, intmath.com/plane-analytic geometry parabola interactive. Okay, so go there if you want to mess around with this site. It's actually pretty neat. So basically what it is a program that allows you to move the focus, the directrix, and a point on the parabola to show the properties of a parabola. Okay, so the distance from P, the point on the graph, to the point F, the focus, is always going to be equal to the distance from that same point P to a point Q on the directrix. Okay, which it says right here. So that comes from the definition of a parabola. So the first thing it asks us to do here is to drag point F, the focus, up or down the y-axis to see the effect on the shape of the parabola. So we'll do that. So notice that the distance from F to P is 4.23, and the distance from Q to P is 4.23. If I move the focus closer to the parabola, the distances stay equal, 2.41, 2.41. The closer I move the focus to the directrix, the narrower the parabola becomes. Okay? If I now move that point away, then the parabola increases slower. We're getting further from the point and the directrix at a slower pace. Okay, so that's what moving F does. It makes the function steeper or flatter. Drag point D up and down. This will move the directrix line up or down. Observe the effect on the shape of the parabola. So now I'm going to grab point D. Okay, and if I move it away, it's having a similar effect. The further the directrix moves from the focus, the slower the graph increases. The closer I move the directrix to the focus, the narrower it becomes. And look what happened when I crossed it. Okay, if we're right on it, then there's nothing exists except a line, which I can't get it exact. But if I move the directrix above, it flipped the parabola over, which would make the first term, the leading coefficient, negative. And now it is decreasing. And notice the distance from F to P and Q to P are always equal. Okay, so that's what moving the directrix will do. And if I moved F below, the same thing would have happened. It flips the parabola underneath like so. Okay? And then the last thing it asks us to do is drag the point P on the parabola and observe the distance D from the focus to the curve is always the same as the distance from the point P to the directrix at Q. So 3.03, 3.03, move this down, move it down, move it down, and then we're at 2.15. No matter where I move it and stop, 9.24, 9.24. This distance equals this distance at all times, regardless of where we move it, they're equal. Okay? And then we can move the graph around too. It says you can move the graph up, down, left, right if you hold down the shift key and drag the graph. So if I hold shift, I can move my graph around. And then I could move my focus down. Okay, the one thing it does not allow me to do though is move the focus off of the y-axis, where in reality we could shift it over. Okay, all right. So that is what this interactive website does, which is pretty cool. Okay, so now let's get to the opening exercise. Are all parabolas congruent? Use the following questions to support your answer. Draw the parabola for each focus and directrix given below. So here's a focus at the point 1, 0, and the directrix is y equals -1. So the distance between the focus and the directrix is 2. So the midpoint will be 1. So that will put a point right here at the point 0, 1, or 0, 0, actually, the origin. Okay, the directrix is y equals -1, focus is 1, 0 is in between 1 and -1. All right, so if I look out here at 2, if I count up 1, 2, and put a dot, I am 1, 2 away from my focus. Count left 2, I'm 2 away from the focus, put a dot, I am also 2 away from the directrix. To go over to 3 on the directrix, I'd have to go, if I went over here and moved up 3 from the directrix, 1, 2, 3, I'd have to move over 3, and that's hard to do at a diagonal. But if I go up to, let's see, this is 0, 0, this is 2, 1, and so on, then when I draw this, it's going to curve up something like this. And then if I curve it over here, this is really tough to draw with my pen. Okay, I will bring in a neater graph in a moment. And then now let's do the same over here. In this case, the directrix is y equals -2, and the focus is the point 0, 2. So this is a y value, this is a y value, that's a distance of 4. The midpoint of a distance 4 is a distance 2 from each end. And if I move down 2 from the focus or up 2 from the directrix, it puts me at the origin right there. So if I go over 4 to 4, 1, 2, 3, 4 would be right here. I am 1, 2, 3, 4 away from the directrix. Go left 4, and I'm 4 above the directrix. So this graph would look like this. So let me bring that in a neater sense. Okay, so this is what it would look like drawn nice and neat. So there are the two examples. So B says, what do they mean by congruent parabolas? This is a really lengthy explanation, so I'll bring it in text. Okay, so the two parabolas would be congruent if we can find a sequence of rigid motions. What are rigid motions? Reflections, rotations, and translations from geometry. That takes one parabola onto the other. We could translate the vertex of the first one onto the vertex of the second one, then rotate the image of the first one so that the directrices are parallel and both parabolas open in the same direction, either up or both down. If the transformed first parabola coincides with the original second parabola, then the two original parabolas are congruent. So now it's asking in part C, are the two parabolas from part A congruent? So the first thing I would do is, actually I'm going to do this with a program. Okay, so I've graphed the two parabolas here on the same graph in GeoGebra. So the first one came out to be f of x equals 1/4 x squared and g of x is 1/8 x squared. And you might be wondering how I got these equations. And it was derived from the fact that the distance of any point to the directrix is equal to the distance of that point to the focus. And that was taught in lesson 33. So if you don't know how to do this, go back and review. You set them equal, you square both sides, and you solve for y. And that gave me these two equations. So as you can see, the focus or the vertex is right on the vertex of the other function. So the two functions only share one point. So the goal to check to see if two parabolas are congruent is to put the vertices on top of each other and check to see that all other points align. And if they don't, you have to reflect, rotate, or whatever, and translate to get that to work. But in this case, now that I have the vertices at the same point, there's no way I can adjust these without changing values. So if I shift one up, I'm no longer going to be on the vertex of the other. So these two parabolas are not congruent. Okay, so these two parabolas are not congruent. They have the same vertex, but different y values for each x in the domain, except for the point at the vertex, which was 0, 0. If we translate the first one somewhere else, then the vertices will not align. If we reflect or rotate, then both parabolas will not open upward. There's no rigid transformation or set of transformations that will take one graph onto the other. Okay, so the question is, are all parabolas congruent? Well, we just gave you an example that is not true, so the answer to this is definitely no. In order to disprove something, all you have to do is find one counterexample, and we have one right on the screen here. So no, we just found two that are not congruent. So E says, under what conditions might two parabolas be congruent? Explain your reasoning. Okay, so once we align the vertices and get the directrices parallel, okay, that's the key. Align the vertices and make sure your directrices, your two directrices are parallel, and the parabola is opening in the same direction. They both have to open up or down through rotations or reflections. The parabolas will have the same shape if the focus and directrix are aligned. Thus, two parabolas will be congruent if they have the same distance between the focus and the directrix. Okay. Okay, page 2 brings us to the exercises. So pause the video, see if you can do these, and come back and check. So it says to draw a parabola with the given focus and directrix. So what I have done is I brought this ruler in. The ruler is perpendicular to the directrix, and it's going through the focus. Okay, so I drew that dashed blue line already. So that's what you need to do. If you really wanted to be accurate, you would have to do a perpendicular line through a point not on the line. That's a geometry construction from last year, but I just lined up my zeros here so that it was, I saw that the ruler is perpendicular. And you could do that with the edge of the ruler as well, putting it right on the directrix and then drawing a line. Okay, that's just a quick. And then we know that the vertex is halfway between the directrix and the focus. And my focus is 15 millimeters from the directrix. So 7.5 would be midpoint. So here's 5, 6, 7.5 is about right there. So here is my vertex. So just to give you an idea as to what happens here, we want a square. And let me just change the color to red and make it thin. I should probably choose the square before I tell it what I want. Red and thin. I don't want it solid. That was a mistake, this one. Okay, so then I'm gonna rotate this thing so it's perpendicular. The sides are right on here like so. And I wanna bring that up to my vertex, or my focus, I mean. I want that corner on the focus, and then I extend this out so that I have the same distance from both. Actually, the easiest way to do this would be a circle. Okay, let me just expand that a little bit. I'm just trying to give you an idea of what we're trying to do. Okay, that's about right there. So if I have a square, what does that mean? Well, it means this distance is equal to this distance. So therefore, this point right here has to be the same distance from the focus and the directrix it would be on the parabola. So then I would move the box over here now and put a dot at this corner. Okay, and now that I've done that, whoops, let's try moving the square instead. Now that I've done that, I do have a parabola that's coming down, and this is very difficult to draw, by the way. And so there is my parabola that would be based off of those two vertices, the focus and the directrix. All right, so number 2, let's do that again. All right, should be easy now. Move this over, put 0 right on like so, and move it up just a smidge. Holding my breath as I do this, and then I'm going to choose a line. And what did I use before? Blue. Okay. Right. Let's use this. Okay, so there is my line of my vertice. My vertex is going to be on this. This is going to be the axis of symmetry. And then I'm going to, let me put my ruler back, count over. This one is 10, 15, 16 millimeters from the directrix. So half of 16 is 8, which is right here. Move this. Here is my vertex, halfway between the directrix and the focus. Okay. So then if I come out here, I'm just going to eyeball it this time. You get the idea. You want to see a square. This distance has to equal this distance. I might be too close. Let's move it out just a smidge and right about there, I guess. And then another one, this distance over here. Same distance here and here. And then my parabola is going to go like so. Okay, so that parabola was sideways. Okay, repeat. Rotate this down, move this to 0 as close as I can, going through the circle or the point. That looks good right there. Let's make it blue and dashed, and I'm going to draw my axis of symmetry. It's to the right just a little, so unfortunately you can't do this on paper, but there it is. Okay. And the halfway point, I'm just going to, instead of measure, I'm just going to estimate. It's right here. And then picture a square. How far over would you have to be this distance and this distance away? Same with this one here, right like that. This parabola is going to curve like so. Okay, so I was more accurate at first, but then once you get a feel for it, it's actually not too bad to do. Okay, page 3, number 4. What can you conclude about the relationship between the parabolas and exercises 1 through 3? Well, if I go back here, I measured this to be 15 millimeters, and then I said this was 16, but actually it's probably closer to 15. And then this one here is also 15 millimeters. So whenever you have a parabola or multiple parabolas where the focus is equidistant from the directrix, regardless of direction, they are congruent. So I'm going to say the parabolas are all the same size and shape because the distance between the focus and the directrix stayed the same. These parabolas should be congruent. So number 5 says, let P be the number of units between the focus and the directrix as shown. As the value of P increases, what happens to the shape of the resulting parabola? Okay. Okay, so to answer this question, I'm going to go back to intmath.com and answer the question using this manipulative. So it says, as the value of P increases, in other words, the distance between the focus and the directrix increases, what happens to the parabola? So I'm going to move F away. And what is the parabola doing? It's flattening out. The further you get from it, let me move this down now. I'm going to move it even further away. The parabola is getting flatter and flatter. It's growing slower. So Putting that into words, I would say as the value of P increases, the graph is dilated and shrinks vertically compared to graphs with a smaller value of P. It appears to get flatter. Okay, so example 1 now says derive an equation for a parabola. Consider a parabola P with a distance where P is greater than 0. So the P can't be negative, distance can't be negative. Between the focus with the coordinates of 0, 1/2 P, and the directrix y equals negative 1/2 P. Okay, what is the equation that represents this parabola? Okay, so this is going back to lesson 33 that I explained a moment ago, and this is what we're going to do. If this is my focus, I'm going to call that F, and this is a point A. And this is my directrix, and I'm going to call that point F prime. Okay, right here. So AF prime is equal to the distance AF, and that's how you start it. So you say the distance AF prime equals AF. That's what we did in lesson 33. And AF prime, the distance is right here. So then I'll replace that with y plus 1/2 P equals, and the distance AF is the square root, the distance formula of x minus x1, x2, which is x, minus x1, which is 0, squared, plus y2, which is y, minus y1, which is 1/2 P squared. Okay, so there's the formula. And then what we need to do is I will put this in parentheses because I need to square both sides. Okay, so I'm not going to do this yet. I'm just going to rewrite this as y plus 1/2 P quantity squared equals, and squaring a square root is the inverse operation and it goes away, and that simplifies this to x minus 0 squared plus y minus, not equals, y minus 1/2 P quantity squared. Okay, so far so good. Now I'm going to distribute this or FOIL it. First term, y times y is y squared. 1/2 py plus 1/2 py is 1/2 py. That's my middle term. And then 1/2 p times 1/2 p is 1/4 p squared equals x minus 0 is just simply x squared plus, and then I do the same over here. Y times y is y squared. Minus 1/2 p minus another 1/2 p is minus 1/2 p y. And then negative times negative is positive. 1/2 p times 1/2 p is 1/4 p squared. Okay. All right. This looks really messy, but it's not that bad. Y squared on this side will cancel with a y squared on this side. Plus 1/4 p squared cancels with plus 1/4 p squared here. And I move this py over here, add py to this side, that will give me 2 py's equal to x squared. Okay, so that cleaned up nicely. And then if I want to get y by itself, I divide by 2p. So the 2p's cancel here and I get y equals, and we like to leave x squared as a number with a coefficient in front of it. So think of this as 1 times x squared over 2p, and I can move that 1 over 2p out in front. So it would look like 1 over 2p times x squared. So there is the equation that represents this parabola. Pretty neat. Okay, this page is just a discussion. I just suggest you pause the video here, or if you have your module in front of you, read this on your own, and I'm going to continue to the next page. So here's the discussion. If you do not have the module, I'll leave it here for a moment. You can pause the video till you get down to this line here, and then I'll scroll for the rest. And then you can pause the video here to read the end part if you do not have this module. Okay, page 5 brings us to example 2. It's a proof. And it says, theorem, given a parabola P, given by the directrix L and a focus F in the Cartesian plane, then P is congruent to the graph of y equals 1 over 2p times x squared, where p is the distance from F to L. So we have a proof that we're going to draw. So here's the diagram off to the side here. This is a parabola that's at an angle because we see that the slope of the directrix is not 0 or undefined. So we know that the parabola is at an angle. Okay, so, and then they give us a point F, the focus, L is the directrix, and then P is the distance from F to L, and therefore the point A is halfway between F and L. So here's the proof. First, we start off by saying, let A be the point on the perpendicular line to L. So A is on this perpendicular line to L. That passes through F, the vertex. I'm sorry, not the vertex, the focus, which is the midpoint of the line segment between F and L. So that's the midpoint there. Okay, so there's step 1. Okay, we're then going to translate A. Here's A right here. We're going to translate it to the origin, A prime, which is at 0, 0, using a translation. Then F, the focus, translates to F prime, and the line L will translate to the line L prime. Okay, so let's just do that first at this point. Okay, so here's the diagram. So what we did is we just simply took all of this and shifted it, translated it over to the origin. So A became A prime at the origin, and the distance from F prime to A prime is equal to the distance from F to A. And L prime is the same distance from F prime as L is from F, okay? So the next thing we're going to do is, okay, so I just moved this down. This is this diagram here. Next, we're going to rotate F prime and L prime about the origin until F double prime is at the point 0, 1/2 p, and L double prime is the line y equals negative 1/2 p. We're guaranteed we can do this because A prime is on the line perpendicular to L prime that passes through F. So the graph will look like this. Okay, so here it is. All we have done now is rotated about A prime, and now that's A double prime. F prime is now had been rotated counterclockwise to F double prime, and therefore L prime got rotated as well, and now L double prime has a slope of 0. Okay, so what did we do? Let's recap. Translate the vertex A to the origin, and then rotate F prime and L prime counterclockwise until F prime is on Y axis and L prime, double prime, is horizontal. Okay, so since P is determined by F and L, the first translation takes P to a parabola P prime such that P is congruent to P prime. The rotation takes P prime to parabola P double prime such that P prime is congruent to P double prime, and therefore P is congruent to P double prime by the transitive property. Then we're going to, let me just do this without pausing. Now by example 1 above, P double prime is going to equal the set of all points x comma y such that y equals 1 over 2p times x squared. That is, P double prime is the graph of the equation y equals 1 over 2p times x squared, which is what we wanted to prove. Okay. Okay, exercise 6 through 9, reflecting on the theorem. So 6 says to restate the results of the theorem from example 2 in your own words. All right, pause the video, see if you can do that. Come back, see what you wrote. Here we go. Okay, so in a nutshell, what that is basically stating is that all parabolas that have the same distance between the focus point and the directrix will be congruent. Number 7 says to create the equation for a parabola that is congruent to y equals 2x squared. Okay. All right. Explain how you determine your answer. So how about this? Y equals 2x squared plus 5. What did I do? I just took that parabola here and shifted it up 5 units. Didn't change its shape. In other words, the distance between the directrix and the focus stayed the same because my A did not change. So that's what we would want to say. The coefficient of x squared, which is 1 over p, or 1 over 2p, I should say. So this 2 is 1 over 2p. All right, so we can find the distance just by taking 1 over 2p and setting it equal to our a. But anyhow, the 1 over 2p cannot change. So 8 says create an equation for a parabola that is not congruent to y equals 2x squared. Well, that's pretty simple now. Y equals 3x squared. Just change your a. Number 9, write the equation for 2 different parabolas that are congruent to the parabola with a focus point 0, 3 and a directrix line y equals -3. Okay, so the way we're going to answer this is remember that your a, your leading coefficient, is the 1 over 2p. And in this case, if our focus is 3, 0, 3, y equals 3, the point is 3 units from the origin, and the line y equals -3 is 3 units below the origin. That is a total distance of 6, and that is our 1 over 2p has to, or I'm sorry, our p is 6. So that's what we're trying to find. Our p is 6. The distance between the focus point and the directrix is your p. And so 1 over 2p is going to become 1 over 2 times 6, which is going to be 1 over 12. So there's my a. So an equation, it says write 2 different parabolas that are congruent to the parabola with a focus point of these and the directrix of y equals -3. All I have to do is write y equals, here is my a, x squared. So there's one equation. And I could just simply shift that up or down, which is the easiest way to do it. So I'm just going to put a y-intercept. I'm going to take 1 over 12x squared, and I'm going to add 3. And so there's 2 equations with the same a, different y-intercept. Okay, there's one example of infinitely many. Okay, page 7 brings us to the end of lesson 34. Go to your problem set.